Okay, so in the last example we did this. Now let's look at a distributed load. You guys should know like what a distributed load is. I'm just going to do another very simple example. We can cover a little bit of superposition because I have quite a bit of time for this thing. The reactions are the same as before. This is P divided by L. This is some length L. This is P over 2. This is P over 2. Now my shear diagram, the beginning and end of my shear diagram is going to be the same because my reactions are the same. Right? And like always, I follow my arrows. And over here, I say I'm going up by P over 2. And then if I go from right to left, like I did before, I say, well, over here I have to go, even though it's pointed upwards, I do the opposite of what it says, and I go down by P over 2. So when I go from left to right, I do what the arrow tells me to do. When I go from right to left, I do the opposite of what the arrow tells me to do. So I go down like here. You're like, okay, that's all fine. But then how do I connect these 2 points? Do you see that I have arrows going downward all the time, right? I have arrows that are constantly going downwards. For every tiny little bit that I go to the right, that I go along this beam, I have to go down by just a little bit. And the amount that I'm going down is constant, right? So if I go down by 0.1 L, then, or if I go to the right by 0.1 L, I go down by 0.1 P. And if I do this constantly, I should get a bunch of points that connect like this. And then we represent that by saying it's a straight line. Now what is the property of this line? If I look at this, the slope of this line is going to be equal to negative P over L. Well, what is this? This is this. Let me use mind-searing red, psychologically scarring red, and in the hopes that this forces you to remember it. It is P over L, or opposite of that. So I hope that you guys see this relation here. The slope of this is this. In other words, my equation for this line, if I just use y-intercept form, I forget what the technical name for this is, but if I look at y equals mx plus b, what is the y-intercept? Y-intercept is b equals p over 2. What is m? I already showed you what m is, right? We go down. Slope is rise over run, so our rise is negative p. We go from p over 2 to negative p over 2. The difference between those is negative p. And we have some run L. So negative p over Lx plus p over 2. And then this is the equation for shear. So I hope you guys are starting to see like where this is going. You can get your equations very quickly. If you know how to look at these diagrams and do these diagrams properly. Remember what I said before, I've been trying to emphasize this, that as you go down, you go up in power. So as you go down, I don't know what you call it. As you go down forms, power goes up. I want to make sure you guys understand it. So if I take the derivative of this, I get w of x equals negative p over L, which is actually this. This should be negative p over L. But normally you assume that your w is already pointed downwards. Normally you assume everything here, like this, you assume is pointed upwards. This one, your W, you normally assume is pointed downwards. Like, it's normal for loads to be pointed downward. It's unusual for loads to be pointed upward. Well, not unusual. It's just not what you guys normally do. There are many cases where loads are pointed upwards, but generally you guys are going to be concerned with gravity loads, dead loads, live loads, things that are pointed downward. And we do not need to get into a philosophical debate about what is up and what is down, what are shadows and what are all this nonsense. Well, yes, if we go from here and we want to find our moment diagrams. The moment diagram is again just the area, right? So then let's look at the area at this point, and at this point. The height is p over 2, base is 0, so I start off at 0. Again, height is negative p over 2, base is 0, so I start off at 0. Then I go over here. What is this? If my moment is the integral of my shear, then my moment at this point, at some point halfway, is just the area of this triangle, right? And my positive, negative. The area of this triangle is p over 2 times L over 2 divided by 2, because that's L over 2 is the base, p over 2 is the height, and then the equation for a triangle is 1/2 b over 2. So my maximum moment at this point ends up becoming PL over 4 times 1 over 2, so PL over 8. And now the question is, how do I connect these two? How do I connect these points? Well, do you agree that if let's look at this section. As I go from here, my moment goes up very quickly at the very beginning, right? But then towards the end, towards the middle, my area is increasing by a very small amount. As I go this way, my area increases less and less quickly, right? Let me fold the paper like this. Like the area is increasing less and less and less quickly until finally it stops. And that's the point we have here. So what does that tell you? My slope at this point should be maximum. My slope is the value of v of x. If I take the derivative of my moment, I get shear. And my shear here is non-zero, so I should have a non-zero slope, right? dm dx equals slope equals v. The dm of x equals slope equals v of x. So I have a positive slope here. I have a positive shear here. Therefore, I should have a positive slope. And if I have my positive axis downward, then I should have a slope that's like this here. Over here, I have a negative slope, right? I should make a quick point. I said that you reverse signs here. That's only for shear. You only do the opposite of what it tells you to do here for shear. So over here, you still have a negative slope, so you don't need to worry about anything. You say you have a negative slope, so you put in a negative slope. And then what happens in the middle? Well, at the middle, my value is 0, so I should have a horizontal point. I should have a thing like this. It should be flat, it should be this. So if I just connect these things, in order for me to have a non-zero slope here and a zero slope here, I must have a parabola. This is a crappy parabola, but that is the graph. So like as you can see, it's really not too hard. Yeah, okay. I'm going to try doing a more complicated example on Let's see if you guys. I'll do a triangular load next because I think triangular is what's a lot of people don't seem to be happy with triangular loads, but it's same principle, same principle. I'll do that in the next video.